tell you as soon as we start with the broadcast. Okay. Good, we are in YouTube now. We can start. So I'm just, it's a pleasure to introduce today here Guillaume Thomas from the Instituto de Astrofísica de Canarias. Guillaume did his PhD on Strasbourg, and he presented the PhD in 2017. And this PhD was done under the supervision of Benoit Famaé and Rodrigo Ibata. And in the topic of how the Milky Way stellar streams can be affected depending on their matter nature. And this is more or less the topic that Guillaume is studying also right now and during his two postdocs. First postdoc that he did in the British Columbia in Victoria from 2017 to 2020. And after that, he got a postdoctoral fellow, Juan de la Cierva, to the IAC Institute in the Canary Islands, in where he is now working. Also, still working in collaboration with many of his old collaborators in the PhD and the new ones he did in Canada. So it's a pleasure that Guillaume is here and we'll talk about stellar streams, distances, and the future with WEAVE and LSST. So thank you a lot, Guillaume, for accepting the invitation to be a part of these IPARCOS seminars. And as soon as you want, you can start with the talk.
Well, thank you very much, Santi. So first of all, I would like to thank you for inviting me to give me the opportunity to present my work. So I was saying, Santi, today I'm going to speak about how we can probe the history of the Milky Way and how we can probe the nature of the dark matter with the next generation of survey, especially WEAVE and LSST. So you can see here different pictures that I've been taking from the different parts of the world that I've been working. So from my native region, Vosges, then from Canada and from the Canary Islands. So one thing that you can see is that I'm going from a region where the Milky Way is more and more beautiful. So I think I choose the top right now. So my scientific question is to understand how such a galaxy like this one was formed. And this question, I have it since I've seen this picture in a book when I was a child about the Andromeda galaxy. And one of the questions that I have since is how such a galaxy was formed, or is it possible that such a thin structure was formed in the universe, which is assumed to be isotropic and almost homogeneous? And then the question is, how is it going to evolve? And so when you go in the lambda CM paradigm, you know that the structure like the galaxy are formed through a succession of accretion and merger, with galaxy eating smaller galaxies, merging with other galaxies of similar size, as you can see on that video from the Virgo consumption. And what you can see is at some point, a galaxy like the Milky Way is so massive that it's just going to attract almost smaller galaxies. And those smaller galaxies that are shown by this different dot here are then going to be disrupted by tidal effects, which means that in that condition, you can see a dwarf galaxy like a sea of stars, and the Milky Way is going to act like the moon on the Earth, and it's going to modify the morphology of the dwarf galaxy. And at some point, this modification of the morphology is so intense that the stars are going to escape from the Lagrange points and forming these really thin structures that are called stellar streams. So depending on the orientation on the orbit of these dwarf galaxies, the streams are going to be more thin, or you're going to get some structure like shells, as you can see here. So now the question is, how can we detect this accretion events? Where is that possible? And what you can see, first of all, is that most of these signatures are not inside the disk, but are really in the outer part of the galaxy, called in a region called stellar halo. So the reason is just because the dynamical timescale in a disk is of the order of a few million years, when in the stellar halo, the distances are so much larger than the dynamical timescale is of the order of several giga-years, which means that these structures are visible for several giga-years, and even when they are not still consistent, especially like when you cannot see the stream like this, the structures stay consistent over almost a full Hubble time in phase space. So the stellar halo is almost 20 times bigger than the disk. So you have here a picture of the Andromeda galaxy. So remember, it was a galaxy that I was showing you before. And here it is, only half of the size of what we estimate to be the stellar halo. So we think that the stellar halo goes up to the end of the real radius. And here it is a survey, it's called PANDAS, that was aimed to observe the stellar halo of Andromeda. That was done on the Canada-France Hawaii telescope between 2007 and 2013. And it just covered half of the real radius of the Andromeda galaxy and the full real radius of the Triangulum galaxy. So the stellar halo is a really, really large and really big, especially saying it's a really big structure, but it represents only less than 1% of stellar masses of a galaxy like the Milky Way or Andromeda. And it is composed of stars that was initially lying in dwarf galaxy or globular clusters, which means that those stars still have the same properties as the initial progenitors, meaning that in general, the stellar halo is formed of old metal-poor stars and mostly coming from accreted objects. However, the inner part of the stellar halo, so for the Milky Way until roughly 20 to 30 kiloparsec, a big amount of the stars are also stars that was initially lying in the disk that have been ejected in the stellar halo, and this is called the in situ population. And the stars was initially in the disk, and the disk have been eaten by due to the different mergers that occur and the different impacts produced by big galaxies like the Sagittarius galaxies, for example. And the stars have been eating and kicking up into the halo. So as you can see, both around Andromeda and around the Milky Way, the stellar halo is not a smooth component. It is actually highly substructured with numerous dwarf galaxies that you can see here, and numerous globular clusters that are especially visible around the Milky Way. And you can also see the thin stellar streams that has this thin structure that you can see here. And thanks to Gaia, we discovered plenty of them around the Milky Way. And you can see the most obvious one around Andromeda galaxy. So this is really interesting because the stellar streams has a direct record of the accretion history of our galaxy, meaning that when you study the properties, the characteristics, you can go back to the history accretion of our galaxy in general, but you can also study what was looking like the progenitors of the stellar streams, meaning that you can also understand the nature of the dwarf galaxies at different ages, at different times. Also, finally, one of the nice characteristics of the stellar halo is also because it's so low masses and it is so big. The dynamic of the stars lying in the stellar halo are as a cinematic dominated by the dark matter. Meaning, if you can measure really precisely the distances, the position, and the velocity of the stars in the stellar halo, you can have a direct measurement of the dark matter distribution around our galaxy. But not only the dark matter distribution, but you can also measure the clumpiness or the granularity of the halo, if you prefer. Meaning that you can measure what is the amount of dark matter subhalo orbiting around the galaxy. And this is extremely important because it's hide inside some crucial information about the nature of the dark matter itself. So I have very often this question to why is it important to reconstruct the accretion history of our galaxy in general? Because we can observe plenty of galaxies in the universe, and the lambda CDM paradigm tell you that the formation of a galaxy like the Milky Way is something which is stochastic, which means that you have intrinsic variations, that you have something which you need to study a large amount of galaxy to really understand in its globality the formation scenarios that we see in the universe. And so for that, I have many answers. Like, first of all, it's our galaxy. So it's kind of human to know where we do come from and where we are going. It's doing just archaeology. It's exactly the same. Also, just because the Milky Way is a typical galaxy, it's a L stars galaxy. So which means that by studying really in detail the Milky Way, we can have information that we cannot see in all the L type star galaxy. So again, the Milky Way is the only galaxy, for example, for which we can measure the dynamic of the stars really precisely, not only with radial velocities, but also with tangential velocities, especially thanks to Gaia now. So again, we can have some information, especially about the dynamic of the object that we cannot have in the other galaxies. Secondly, it's also really interesting to trace where is the dark matter in our galaxy, again, because we have the full dynamical components that we don't have in other galaxies, which means that we can really probe in detail the dark matter distribution, but also the granularity. And again, we can explore the nature of the dark matter because, as you can see, depending on the type of dark matter, so for either a cold dark matter, a warm dark matter, a superfluid dark matter, I don't know what kind of particle you want, you will get different level of granularity, different level of distribution around the galaxy. As here you can see, for example, in a cold dark matter universe, you expect to get plenty of substructures with a halo of dark matter that we think are going to go up to the size of stellar systems, when in the warm dark matter universe, because you have a higher dispersion before recombination of the dark matter particles, you get less low mass substructures, and you typically get a cut of structures of around 10 to the power 6, 10 to the power 7, depending again exactly on the mass of the dark matter particle. So one of the problems that we have when we want to study the stellar halo is that if you want to study the stellar halo of our galaxy, you need to observe the full sky. And not only you need to observe the full sky, so the 400 square degrees of the sky, but you need also to go really deep, because contrary to the Andromeda galaxy, if I go back here, you can just by some statistical argument, by some geometrical argument, counting the number of stars at different ridges. However, we are lying inside our galaxy, which means that if you want to understand, for example, just something as simple as the profile of the stars, you need to be able to measure the distances of that stars. And those stars are really far, especially if you want to get plenty of them and to get reliable information, you got to go really deep in magnitude, which means that we need large photometric deep surveys. So here we have a list of the different large surveys that have been done so far. So it's just optical surveys, and the reason is just because the stars in our galaxy are mostly visible in optical. It's where you have the maximum of the transmission of light. So I think that everybody knows the SDSS, which was a large survey done in the northern hemisphere, done in the U, G, I, and Z band. Now you have the Pan-STARRS 1 3Pi survey, which have been conducted from a telescope on Big Island. That have observed three-fourths of the full sky in G, R, I, Z, and Y bands. So you go a bit more in that cases in the near infrared, but you don't have the near UV bands counterpart, which is the U band. In the south, you get DES, that was again the same filter, but just for 5,000 square degrees. And you get more recently the IPARCOS CAM Subaru strategic program, which was again observed in G, R, I, Z band. So it was a really deep survey, going up to magnitude of 26, 27 in G band, but covering only 680 square degrees mostly in the northern hemisphere. Then you have Gaia as well, because Gaia is not only an astrometric survey, it's also really precise photometric surveys. And one of the advantages also is that it's covering the whole sky, which means that you can get this G, BP, and RP band for a really large amount of stars, more than 1.8 billion. And you have also another survey, which is CFIS, and CFIS is the name for the Canada France Imaging Survey. And it is a survey which is conducted in the U and R band, and it's covering more than 10,000 square degrees. And the goal, at least for the U band, was to be able to give an information that we are lacking in SDSS, which is a U band. And I will show you why the U band is extremely important in general for sciences, because it's easy to use to identify stellar population just with photometry. It's a really good tracer for the metallicities. It can also help you to disentangle different type of stars, but also to get photometric redshift. And CFIS was initially built as a follow-up for the Euclid Space Telescope to get photometric redshift of galaxies. So there is other surveys that have been conducted for the same purposes, but in other bands. So especially you have the I and Z band from Pan-STARRS, not the survey, but the telescope. You get also some bands that have been observed by the Subaru telescope, especially in the Z band. And in the northern hemisphere, the G-band will be given by the GEDI G-band, which is a survey which is going to start being observed from the Raval-Hombre telescope really soon, normally. So CFIS, no, CFIS is a kind of a weird survey because every 2 years we have the habit to change the name. So no, we have some collaboration with PAN-STARRS, so the telescope, on WISHES, which is a surveys that the Japanese community provide to us to give us a Z-band on part of the G-band. And the goal is to make a survey called UNIONS. So it stands for Ultraviolet Near Infrared Optical Northern Sky Survey. And so it's observed from the U to the Z band with really high precision, with an image quality as good as what we will have for LSST. So for the moment, you can see that UNIONS will be the best survey that we'll have in the northern hemisphere for at least the next decade and even beyond. So UNIONS is exactly the same as LSST in the northern hemisphere, except that we don't have the time domain because we don't observe repeatedly the sky as we do LSST. So one of the goals that we hope is that when the GEDI will join, we'll be in touch with them to ask if they want to join as well the collaboration. So it will also give an opportunity to the Spanish community to get access to this amazing amount of data that are for the moment not as used as what it should be, because they are mostly made they are mostly available for the Canadian, French, Hawaiian, and Japanese community. But we hope that if GEDI want to join as well, the Spanish community will be able to get access to UNIONS, on which you can already prepare the next LSST data as well. So CFIS, as I was telling you before, I've been observed on the Canada-France Hawaiian telescope, which is it's a really old telescope of 40 years old, but still doing amazing science. And CFIS is composed of two bands that observe two different areas. So the U band is shown by this blue area here, and will cover at the end of the survey 10,000 square meters. And the air band, which is shown by this air band here, by this red band, sorry, is going to cover 5,000 square degrees at the end of the surveys, with a really amazing image quality, with a minimum required of 0.8 arcsecond for seeing, with a mean of 0.6. And the reason is just because it was initially designed to do weak lengths galaxies. So we have a really amazing image quality in CFIS in general, but especially in the air band. So here we have the current coverage of the U band in galactic coordinates. So in purple, it is what we should have at the end of the surveys, and in green, it is what we have currently. And as you can see, even if the surveys have started in 2015, we are still a really low amount of coverages, just because we have been extremely unlucky between a problem of weather. We had really bad weather over the last 2-3 years in Mauna Kea. We have been also seeing some failure of the camera. We have seen some problem with it. Also with COVID, we have got also volcanic eruptions, and as well as the problems that everybody knows in Hawaii with the First Nations there. So, but anyway, the coverage is going to be made because it's really a strategic surveys, both for Canadian and French communities, but as well just for Euclids. So there is a really big pressure, and we know, and we have been extended the surveys for already 2 years. So at the end, we are sure to be able to cover it. So CFIS compared to SDSS, which is the other U-band, large U-band available so far, show a really big improvement. Here you have just, for example, images from the Leo-P dwarf spheroidal galaxies, which is a star-forming galaxy. So it's really popping up in the blue band, which is the U. And you can really see the improvement between CFIS and SDSS with really great amount of stars, but as well in the G band, which was deeper than SDSS, as you can see here. And this is due to the U band of CFIS being 3 magnitude deeper than SDSS for the same quality, for geometric uncertainties, but also for better image qualities than SDSS. Again, just because we are on Hawaii and the image quality there is amazing. In the background, you have also the images of the triangulum galaxies, again showing the U band with the low surface brightness reduction. So you see again the really high image qualities that we have observed from Earth again. So it's really amazing to see this. For those people that prefer column magnitude diagram, as I do, here you have just another example showing a really big improvement from SDSS to CFIS. So it is Hercules globular cluster M13. And here you see really clearly that with the U-band of CFIS, we can get a tighter column magnitude diagram. And when you do a column magnitude diagram using the U-band of CFIS and the G-band of Gaia, you see that you get something which is really thin and which is in terms of thickness almost as good as from HST data, which means again that we can really do really amazing science with these surveys. And one of the things is, for example, for some globular cluster, we are able to see the two different giant branches, which is due to the different molecules, especially nitrogen, present in the stars. So you can really see these two bands that are just being observed so far with HST data. So with these big surveys, there's plenty of work that you can do. One of the easiest things that you can do to study the stellar halo is to measure its density profile. So just to measure, basically to do a star counting, to measure what is the profile of the halo. And there is many purposes. Is that first of all, you can compare it to cosmological simulation. You can compare it to the profile of the dark matter. You can compare to profile that we are seeing in other galaxies as well. And finally, when you get the profile and when you have also at the same time the cinematic of the stars in the halo, if you assume that the galaxy is in equilibrium, you can also measure the mass of the galaxy, which again tell you really big information about its history and its mass assembly as well, and how it's compared to other galaxies. So the problem of that is the stars in the stellar halo are really far. They stand from typically 15 kiloparsec to almost 300 kiloparsec, which means that unfortunately, even at the end of the Gaia surveys, the parallaxes will not be precise enough to measure the distances of the halo stars. So you need to find for other tracers to measure the distances. And in the past, what I've been doing is to use stellar candles like Aerial or blue horizontal branch stars, BHBs, that are easily identifiable and that are also with a constant absolute magnitude. So you can use them to then measure the distances of the stars and to measure the profile of the halo. So I'm not going to speak about on the aerial arrays. I didn't use them because, as I was telling you, we don't get the time domain, and aerial arrays are variable stars that are easily identifiable when you have the time domain. So with LSST, we'll discover plenty of them or confirm plenty of them. But for the BHBs, they are easier to detect because, as you can see, if you use U-G, G-R color, you can really see the main sequence of the giant stars, and then here you see really clearly this coma shape, which is actually standing for the ape-type stars. So mostly blue strikers and blue horizontal branch stars. So just also again to show the really high quality of CFIs, you can really see here the white dwarf and white dwarf with different atmospheric composition. In that case, you see the track of helium stars, which wasn't as visible in the CSS. And again, the advantage of the U-band is that you can also disentangle the QSOs with really high precision. So with the BHBs, one of the problems is even if they are easily identifiable by this coma shape, you still have contamination by other type of stars, which are the blue strikers. And here you have the spectra for these two stars. So in blue for typical BHBs, and in red for typical blue strikers. And what you can see is even with broadband photometry, you can still disentangle those stars because you have the Balmer jump here, which means that you have really strong differences in terms of flux when you do a color diagram, especially in the UMHG, because you have the Balmer jump, which means that you have this difference of magnitude between these two types of stars. But as well, when you do I minus Z color, because you see the passion lines there. So even if it's not as visible for the Balmer line, it's actually this passion line is sensitive to the surface gravity, and the blue strikers have a surface gravity similar to a dwarf when the BHBs are giants, which means that they have a lower surface gravity than the blue strikers. And so you can really identifying them and differentiate these two types of stars using a U-G I-Z color, basically. So it's what I have done. I have separated them with really high accuracy, better than what I've been done in the past. We get almost 80% of completeness on only 30% of contamination. So with statistical model behind it and taking into account the variation of completeness of the different surveys that we have been using. So in that case, it's the U-band of Cepheids, GRI-Z band of pan stars, 3π. We have been able to study the shape of the halo up to 250 kiloparsec, and we observe that the profile of the stellar halo is actually well represented by a broken power law with a break around 40 kiloparsec, with a really steep inner profile with a slope around -4 up till from the inner halo to 40 kiloparsec, and then with a shallower profile with a slope of -3. So first of all, you can see that the profile that we see for the stellar halo is steeper than the profile of the dark matter halo, which again is normal. When you have a galaxy which starts to be disrupted, you start to disrupt its dark matter halo rather than its stellar component, which means that the galaxy has a time to sink at deeper in the Milky Way potential before starting to be disrupted by stellar components. So one of the things also which is extremely striking is that when we compare to other type of stars, you can see that we are really similar to the profile that have been found by Fukushima, which has been done using BHBs again. So this has been done with the Subaru strategy program, which is really deep. So they are able to go slightly farther than us, but they are not as large as us. We are typically at the time of that study was done, we were roughly 10 times bigger than them. So at least we see some consistency. It's not because they was observing a peculiar region. It seems that the profile is almost everywhere the same, at least until the distances. And when you compare to previous work that have been done by Alice Deason, you see that Alice Deason was in agreement with us. Well, showing something a bit slightly different in the inner halo, which again is not completely unsurprising, because in our cases we have a problem of saturation of stars. So that's why also we didn't really trust the result bit before 20 kiloparsec. But at least after 60 kiloparsec, she found that there is a big drop in terms of density. And you can see it's really different than what we have found either with the Fukushima study or my studies. And the reason is just because she didn't took well into account the completeness of the surveys when you go at really deep magnitude. However, something which is extremely striking is the differences that you observe with RLI rays. So the RLI rays are shown by this blue profile or this purple or this pink profile, and the RLI rays are really precise, as you can see that after 40 kiloparsec, the profile are really different. And so one can wonder, how is that possible that two population of stars that are supposed to trace the same type of stars, meaning an old meta-pool population, or these two population, or these two population of stars can have different profiles. So it's maybe even better to see in that cases, when you plot really and you normalize by the density, you can see really that the BHBs has a really clear different profiles than the RLI rays. And so one can wonder if it is a problem of selection, either by the BHBs or the RLI rays. For the BHBs, as I was telling you, you still have some contamination. So maybe we are actually seeing the contamination in the distances, or RLI rays, you need to detect them via density variation. But when you go farther in distances, you are still dominated at some point by the uncertainties in the measurement. So it's harder to measure the flux variation. So maybe there is a problem of selection in one or maybe the two different stellar population, or maybe it tells something subjacent inside of the different origin of these populations. And the problem is that even if these two populations are really great and really good tracer in general, this is sparse population. They are not really numerous. And so it's really hard to be able to measure the profile. For example, for the BHBs, after 150 kiloparsec, we are just speaking of measuring the profile of the halo with 10 BHBs over 4,000 square degrees. So in terms of significance of measurement, I have seen better. So the question is, can we use other stellar population to do the same and to also see if there is any variation with metallicities, for example, or with different ages of population? So what you would like to get is this kind of map. You would like to get a metallicity, a 3D chemical distribution in the Milky Way, but not only up to 12 kiloparsec, but going up to 100, 200 kiloparsec, really far in the halo, where you are really going to see the past of the past accretion events. So it's been done with SDSS, but just up to 12 kiloparsec, assuming that all the stars was main sequence stars. And the problem to do that is you need the distances of the stars. So as I was telling you, distances are tricky to get, but you also need to get metallicities. So for the metallicities, you can get spectroscopic data, but they are really expensive to do. And it's not tomorrow that we'll be able to put a fiber to any stars. So if you don't want to deal with this really crazy completeness function, you need to use photometry. Another problem is also to get the distances. If you want to use photometric distances, is either stars a giant or a dwarf, because these two types of stars have different tracks, color spaces. And so you need to be able to identify the stars before. So how it was made for this study, it's something kind of, I will call classical. So people were just measuring the photometric metallicities in U minus G, G minus R. And as you can see, this color space, it's really sensitive to the metallicity. So here you have real metallicity data obtained by Segway. And here you have the model that have been fitted on that. So you can just fit a polynomial model on that color diagram to estimate the metallicity, assuming again that all the stars that you have there are main sequence. And then the problem is when you have your metallicities, you assume the age. So typical stars of the halo has an age of 10, 11 gigayears. So you just assume these ages and you finish with a stellar, single stellar population like this. And the problem then is to know how you can get the distances. So people were just going in the color, selecting a color, saying, oh yeah, so this is where it's crossed the main sequence. So it's this typical absolute magnitude, and then you just compare the apparent magnitude to the absolute magnitude to get the distance of the stars. The problem is that you see that at the similar color, you can get another type of stars, meaning a giant, where the absolute magnitude is completely different of several orders of magnitude, and these differences between main sequence and giant is higher when you go in the radar area. As you can see, you have even several more type of order of magnitude of differences. So it's tricky in general. And moreover, if you assume that all the stars are main sequence, just because they are more numerous than the giants, for the few giants that will fall in your color cut, for example, you're going also to misidentify the magnitude because you have an offset of typically 0.16 depths of magnitude of metallicities. So to try to resolve this, I used a really powerful machine learning techniques to be able to use all the amount of broadband photometry that we have, and to try to, first of all, classify stars as dwarf and giant. So to know if it is more stars like this or stars like this one, using just the photometry. And then when I know this, so for that I was using a random forest classifier, which is just a suite of questions saying, is that star between that color and that color? Yes, no, yes, no, yes, no. And use that for several trees. And then at the end you have a forest, and you just do a majority pooling between these different trees to know if a star is most likely a dwarf or a giant. Then I have two different pipelines, one for the dwarf, one for the giant, to determine the metallicities using the photometry, again, because the U-band is really useful to get metallicities. And the reason is just because you have plenty of absorption line of metallicity feature absorption line in the U-band, but also then to determine the absolute magnitude in the G-band for the dwarf and the giants, and then to measure the distances directly. So for these two different parameters, I was using an artificial neural network. So a neural network, I don't know if you know how it is working, but it's not a black box that everybody imagine it is, but it's something rather really simple. You start with your input. In our cases, it was the color of the stars, so all the different color possible, U minus G, U minus R, and so on. And then you have different layers, and each of the node of these layers, you're going to do a linear regression in the type A, type X plus B. But you see that if I do that for each of the layer, at the end I just finish with a classical polynomial, right? You're just going with a typical A type X plus B powers the number of layers that you have. So to be able to go outside this linear regime, we use what is called an activation function. So it's have different profile, but typically is to put something between 0 and 1 or 0 and maximum. And doing so, then you just do a large number of layers. And then the question is, what are the different parameters A and B for each different node to be able to get in output something which is similar to what I have, to what I want to train on. So in our cases, we were training on photometric data, but that have Segway counterparts, because with that, we can select the stars that are dwarf or giant using the surface gravity provided by Segway. But we have also metallicity measurements. So we can use the metallicity on Segway to train on those stars with spectroscopic counterparts to be able to find the track between the photometry and the metallicities. And when you have found this track, to apply that to all the stars, not only the ones that have spectroscopic counterpart, but to all the photometric stars. So in the case of Cephis, it's more than 21 million of stars. For the absolute magnitude, we are using the stars that have Gaia counterparts, and that have really precise parallaxes. So with those stars, we were able to measure really precisely the distances, and we were training the machine learning on those stars to then apply it to just determine the absolute magnitude just using the photometry rather than using the parallaxes, which are, again, really imprecise. So for the classification dwarf giants, we had something which was really good. So for the dwarf, you see that we have really good purity and completeness, but actually it's not really relevant in that cases, because if I was assuming that all the stars that I was giving in the training sample was a dwarf, I will get a completeness of 100%. I will recover all the dwarf because I say all the stars as dwarf. So obviously all the actual dwarf are inside this catalog, but I will get a purity of 86%, which is not so much different than 93%. Well, a couple of percent of differences. But where it's more interesting for the giants, because they just are corresponding to 14% of the sample. And we see that in that cases, with the machine learning, we are able to get a 70% of completeness, which means that we are able to cover almost 6 over 10 giants. And actually, this sample is really pure. We get more than 70% of the stars that we said are giants that are actually giants. So it's actually a really amazing number, because in the past, people were thinking it was impossible to use broadband photometry to this kind of differentiations. In terms of metallicities, we found that typically 0.15 dex for the dwarf and 0.17 dex for the giants. So we get, again, really precise photometric metallicities just using the U-band. We are able to give metallicity measurement until roughly -2, -2.2 for the giants. And then for metallicity below that, we reach a floor, because the broadband photometry, even if it's amazing to give metallicities, at some point you are not able to differentiate a star with -3 or -2 metallicities, just because they are too close in a photometric track. In terms of distances, we were able to get 16% of relative distances precision for the dwarf and 25% of the giant. So in comparison, for the previous studies that I was showing you with BHBs, we estimate that the BHBs has a precision of roughly 10%. So again, you see that we have really good precision on these different type of stars. And now with the new Gaia EDR3, we are even able to achieve a better percentage in terms of relative distances measurements. So with that, you can do plenty of things. So first of all, we are also being able to compare with globular cluster. So to get an independent sanity check, we just seen, well, we have globular cluster. We know the distances of globular cluster. Are we able to recover the metallicity and the distances of this globular cluster just using our algorithm for the few globular clusters falling in the Cephis footprint? So here we have a color magnitude diagram using distances from the literature for 2 globular clusters. Here you have the color magnitude diagram when you invert the Gaia parallaxes, and in gray it's just the reference one for just for comparison. So it's something that you should not do when you invert the parallaxes when they are really imprecise, because you're really likely going to underestimate the distances. So you have a really nice paper from Xuri about that 2 or 3 years ago. No? And here we have the color magnitude diagram that we predict with our algorithm, and you are able to see that we are able to recover really well the track. The only thing is that we are not able to recover the subgiant just because we don't have a classification for the stars. It's already hard enough to differentiate between a dwarf and a giant with the photometry, so that's why we didn't try to push to get subgiant. Again, because they're also really not numerous. So it's in our case, it's not really a big problem. So with that, so far, we have a catalog of 21 million of stars with photometric distances and metallicities in the Cephis footprint. And with that, we have been able to construct this kind of map that was similar to SDSS. And just to give you an extent of to what is the amount of precision that we are able to achieve. which is a comparison to the previous work from Zurich, from Zurich and Ivesic that was doing that with SDSS. So you see that we are able to reach until 60 kiloparsec. And this again is thanks because we are able to identify giant with the photometry. But even if you're just taking the dwarf into account, we are able to go up to 30 kiloparsec instead of just 12 kiloparsec in the cases. So what you can see here is that in this mean metallicity map, you can see an increase of the metallicity, but this actually is artificial just because we are limited by the apparent magnitude of Gaia. And for a given apparent magnitude, you're going to get more metal-rich stars and metal-poor stars just because the track of the main sequence stars for metal-poor metal sequence stars has lower absolute magnitude than for metal-rich stars. And so you're just artificially going to increase the number of metal-rich stars in larger distances. So this ring is artificial, but anyway, what you can see is that you can clearly see the disk and the decrease of metallicities. And it seems that even with the giant, the decrease of metallicities is still visible, which is in contradiction with what I've been seeing in the past. But again, this is something on which we are still working on right now. So with that, we were also able to identify new structures, like especially new stellar streams. So it's helped me to identify a stellar stream around the globular cluster M92. So we discovered a stellar stream emanating from that globular cluster with 17 degrees from the sky, with 42 parsec wide, which is 1.4 times the tidal radius of the cluster, which is typical for stellar streams. And we find that the mass in the stream is corresponding to 10% of the current mass in the cluster, which means that you have typically 9% of the total mass of the progenitors that are escaping the globular cluster. And here you have some stars that have been able to validate the presence of the cluster thanks to the catalog of distances that I was showing you of metallicities, but also with Gaia parallaxes. So when I was trying to reproduce that globular cluster with simulation, it seems that to reproduce that stellar streams, the globular cluster have to be disrupted really recently, otherwise it will be completely disrupted. And for that, we put a constraint on the age of the streams, and have been formed less than 600 million years ago, which is really young, especially when you compare to the age of the cluster, which is of 11 giga years. So this forced us to ask us the question, where was the globular cluster of the other 10.5 giga years? And how is that possible that the globular cluster wasn't completely disrupted before that? Even if you take into account the really recent massive accretion, like GAN said, sausages, things like that, we're just speaking of objects that have been accreted 8 giga years ago, so it should have a different origin and something should have modified its orbit. So there is several ideas behind it to explain this scenario. First of all, it's because the globular cluster passed towards the galactic center in the less than 1 central inner kiloparsec of the Milky Way. We should take into account that there is a bar, and my model didn't took it into account. So it's possible that the orbit of the cluster has been changing just because the bar have been exchanging angular momentum to the globular cluster. It's also possible that there is some weird effect due to the central black hole that I didn't put also into account. It was a very simple model that I was making, by the way. Another explanation is that M92 was a globular cluster that was orbiting around the dwarf galaxies, and that dwarf galaxies is now completely disrupted, but the globular cluster is still living. Or another explanation, because M92 is a really special cluster with really metal-poor globular cluster, but with not a lot of high resolution, unfortunately. It is possible that M92 is actually the core of the dwarf galaxies, so the rest of the dwarf galaxies is not completely disrupted, and the M92 is just the remnant of that dwarf galaxies. So we are still exploring this because this is really recent results, and we hope that with WEAVE we will be able to get better data, to get better constraint about the nature of this globular cluster. So also with the catalog of distances, we have been able to extend the detection of already known stellar streams emanating from the globular cluster 5466. So here you see all the giants in the CFIS footprints. And then we did proper motion cuts, metallicity cut, and distances cut to be able to identify the stellar streams that is visible here. So it's a job that has been made by my student, Jacqueline Jensen, which we just submitted the paper a few weeks ago. So we have been able to extend the extent of the streams, But mostly what we have been able to see is that there is a strong variation of the distances in the streams, meaning that there is an heliocentric distances variation along the stream ranging from 10 to 30 kiloparsec. So again, this stellar stream is extremely great because it's one of the fastest stellar streams that we know so far. And so meaning that if you are able to measure the kinematic of those stars, you will be able to measure really precisely the dark matter distribution at different radii. The reason is because the total amount of energy is conserved along the stellar streams. So if you are able to measure really precisely the position, the distances, and the velocity of the stars along the streams, you can measure the variation of the potential in the streams. So that's why stellar streams are really interesting. For the case of M92, the apocenter is only of 11 kiloparsec. So we are not so much able to measure the dark matter content, but it's a really good probe to be able to study the inner part of the galaxy, because as I was telling you, it's going in the inner one kiloparsec of our galaxy. And for me, it's really striking that an object which is really far from the disk can actually tell you something about the inner part of our galaxy. So one of the things also that we aim to be able to study soon will be the impact of the large energy infall. It's been recently shown that the LMC could be really massive with a mass ranging from 1 to 3 times 10 to the power 11, which means that you have plenty of perturbation that you should have in the halo with a dynamical friction tail beyond the LMC, but also attraction of the disk of the Milky Way, which changes the barycenter of the galaxy, which generates also a collective response of the halo, so a collective perturbation, I would like to say, in the dark matter halo, which should be visible in the stellar halo density, but also in the cinematic. So just to show you, for example, we should be able to see that with CFIs, not in the southern hemisphere because we don't have any data, but we should be able to see at least a big amount of the perturbation in the northern hemisphere, especially while the tail of the dynamical friction, but also the global motion of the halo, as you can see here, with the overlapping of the footprint. So the LMC has also really big impacts on dwarf galaxies on the local group. So here it is a paper that we submitted recently with a team in the ISE with Giuseppina Battaglia, Salvatore Taibi, me, and Tobias Fritz, where we study the proper motions in the Gaia EDR3 area of local dwarf galaxies, and we have been able to assign some of them to being emanating from the Magellanic system. So I think I'm going to really quickly finish on that. Sorry for the time. Just to speak really roughly about WEAVE, because I'm a dynamicist, I still need radial velocities. And as you know, all of you, radial velocities are really expensive to get. So WEAVE is this really large survey that is going to be conducted on the William Herschel telescope on La Palma, and is going to cover a really large area, 10,000 square degrees, with a lot of stars observed, especially in the galactic halo. We aim on 500,000 of stars observed in the stellar halo. So it's going to observe in high resolution and in low resolution, which means that we'll be able to get metallicities, velocities, alpha bonances for a lot of stars, but also individual elements for plenty of stars in the stellar halo and in the disk as well. So this is a really perfect tool for galactic archaeology and galactic dynamics in general. So with that, we will be able, for example, to get radial velocities for the stars along stellar streams that we have been able to detect recently with Gaia. We will be able to characterize the progenitors of the structures, to get star formation history of those progenitors, but also to measure the granularity of the dark matter halo, because we expect that when you have a dark matter subhalo crossing a stellar stream, you're going to get density variation. But the problem is that density variation can be tricky to observe because it can be due to millions of impacts, either due to the surveys that have been done to observe them, like in SDSS. Just the inhomogeneities in the survey can generate this, it can explain this variation of density. But we think, and it has been shown with simulation, that it's also gives some perturbation in velocities, and these perturbation velocities should be really characteristic of the dark matter subhalo. So that's why we aim and we hope that with WEAVE we'll be able to really confirm the presence of dark matter subhalo, which will give us a constraint about the nature of the dark matter, either to rule out one dark matter model, or at least to give a minimum mass, a mass constraint on the mass of the dark matter particle itself. So yeah, also we will be able to identify new structures visible in phase space, like have been detected recently with the galactic sausages and Sagittarius. And finally, as I was telling you again, distances is a key point for this kind of studies. And so just to show you that spectroscopic photometric distances, when you use machine learning, which basically was the same method that I was doing with photometric distances, if you use that with spectrophotometric distances, we can get really precise distances. And here it is an example that I have been doing with Segway. So here you have the colorimetric diagram that you have in Segway when you use really good Gaia parallaxes. And here it is what I predict with the machine learning. So you see that not only you are able to reproduce it, but you can even improve it because you don't see this double sequence of not really well. When you use the machine learning distances, you can really see these double sequences in the halo, but also in the main sequence stars, as it has been shown with really precise Gaia parallaxes really recently. So in typical, we have 14% precision distances with this method. We hope that we will have even better because it will be more precise with higher resolution. Also, this is an upper estimation of the precision that we have, again, because we think actually we are better because we are improving the colorimetric diagram. So in conclusion, here it is. Photometric distances, photometric surveys are really amazing. The profile beyond 40 kiloparsec is very different between two closely related populations. We have been able to see that the profile seems shallower at larger distances, but we need more stars to be able to confirm this. We also have discovered plenty of new stellar streams, which are going to give us really strong arguments or really strong probes to probe the nature of the dark matter, but also the dark matter distribution around our galaxy. And so in conclusion, if you have something to retain from that talk, it's that precise distances are crucial. It's really hard to get them for stars in the stellar halo. Gaia is not good enough to give precise parallaxes, so we have to find other tweaks to be able to do that. And also that we need spectroscopic data, because if you want to study the nature of the dark matter, you need to get a cinematic of the stars to be able to do dynamic and to study not only the profile of the dark matter in our galaxy, but also to study its granularity and to be able to know what is the nature of the dark matter itself. So in conclusion, we still have plenty of work to do to understand our galaxy in history. So thank you really much.
Thank you a lot, Guillaume, for this very clear and very interesting talk. I have some questions, but we will leave first time for the people in the audience to make their questions. Please just raise your hand, and when you start talking, please tell your name and also your institution. So we can start with the questions. Okay, for the moment, I will just break the ice with my first question then. You were talking about distinguishing between these different natures for the dark matter. Yeah, I think you probably mean that depending on how hot the dark matter is, you will have more or less substructure, so you expect more or less perturbations in the streams. What about not having dark matter? You think there is any prediction with the streams on some of the theories that do not include dark matter?
Yeah, so actually I'm the specialist of that because I'm the only one that made so far a model of stellar streams in modified gravity model like MOND. So yes, there's prediction, and there is really interesting prediction, especially in MOND you have an effect, which is a really large scale effect, which breaks the strong equivalence principle, which means that when you have an object, you cannot really disentangle them from the external acceleration. So normally in Newtonian dynamic, if you don't take into account the tidal effect, you can disentangle acceleration produced by the Milky Way from the acceleration produced by the cluster. So you can measure the internal dynamic of the cluster. It's not influenced by the Milky Way. In MOND, it's not the case. In MOND, depending on where you are, your Milky Way is going to get a really big impact on the internal dynamic of your globular cluster. And this modifies the shape of your globular cluster, but also modifies the length of the streams, things like that. So there is things that we can do to be able to rule out MOND or to rule out dark matter with that. So stellar stream are really amazing also for that, but just also globular cluster in general. So, and if you are able to probe, for example, that you can observe this effect, you can put a really big problem to general relativity, because one of the pillars of general relativity is a strong invariance problem. So yeah, it's possible that with alternative theory, we can get something also really interesting to predict. So stellar stream in general is good. Sorry.
Yep. Thank you for the answer, and also probably detecting or not the wake and the collective effects will be a proof of having or not dark matter halos.
Yeah, this I'm a bit more skeptical about it, because in MOND, due to this really large scale effect, we just submitted a paper with a student that I have in Strasbourg that you can actually get a really weird Milky Way shape in MOND when you take into account the galaxy cluster like Virgo or the Laniakea, for example, have really big impact on the internal dynamic of the Milky Way itself. And it can generate, when you take also into account the LMC, an effect really similar to what you have actually in the CDM. So I think that detecting or not the wake or the strength of the length of the wake can actually tell you more about the nature of the dark matter itself, meaning that in warm dark matter, you expect to get a lower wake than in cold dark matter, because you are higher dispersion. So you expect normally naively to get a slightly different distribution profile. But also, for example, if you go back to the superfluid dark matter particle, which is this particle from Justin Curry and collaborators, where you have a Bose-Einstein condensate type of dark matter, you don't expect to see this kind of effect or to see something which is really different. So there is no simulations that have been made so far with that. But with mathematical calculation, you expect it to get something which is kind of different. So being able to detect this shape and to be able to quantify this shape and the strength of this perturbation due to the LMC can tell you a lot about, much more about the nature of the dark matter and tell you if dark matter exists or not, I guess.
Okay, thank you. I have another question, but maybe now somebody in the audience has another one that they want to make it. No, for the moment I cannot see any. Okay, so I will proceed with the next one. The next one, I don't know if you mentioned it, but in the system you are using, the new method you are using to compute the metallicity, do you have a limit for the lower metallicity you require for this method to work?
Yeah, so, well, as I was telling you, we cannot really, at some point, we have a floor that we see between -2 and -2.2. So -2 for the dwarf, -2.2 for the giant. And below that, all the stars that are actually more metal poor than that have a metallicity which is completely unmeasurable between -2 and -3 typically. So when our code gives a metallicity lower than -2, we can just say it starts with a metallicity lower than -2, but we can't really say something about it. And the reason is just, again, we use broadband photometry. Yeah. No, this is not a problem.
Sorry.
No, that's not a big problem for us, because most of the stars in the halo are between -1.5 and -2. And for the most metal poor stars, there was an other photometric survey called Pristine, which observed in calcium H and K, which now cover 5,000 square degrees, which is extremely useful. And because it's really sensitive, in that case, calcium H and K, which is extremely sensitive, especially in the metal poor region, you can get photometric metallicities really precisely for stars between -2 to -4. So actually, we are complementary with them, and yeah, we work a lot with them as well.
Perfect, thank you. So I will leave a last opportunity to the audience to make additional questions. No, so okay, so we can leave it here. Thank you a lot, Guillaume, for the nice talk, and also for the description of this very interesting work and future work you are planning to do. And hope to have you again in a future seminar with a discussion of the work you are doing. So thank you a lot for accepting the invitation and see you soon.
Yeah, well, thank you for giving me this opportunity, and I hope to be able to go to Madrid at least once to be able to visit your
institution. One.
Exactly.
Perfect. So thank you, and I invite the people to next week for the next astro-seminar, IPARCOS-astroseminar. Next week it will be on Monday, and it will be the presentation of the Agora results at 10 o'clock in the morning. So you are invited to come also on Monday's IPARCOS-astroseminar. Thank you a lot and have a nice weekend. Thank you, Guillaume.